Imagine a regular crystal. Think of a diamond or a simple grain of salt. If you could zoom in, way down to the atomic level, you would see atoms arranged in a repeating pattern. This pattern extends through space. Left, right, up, down. The structure is orderly and predictable. This is what makes a crystal a crystal. It has a structure that repeats in space. For centuries we thought this was the only kind of crystal that could exist. We live in a universe of 3 spatial dimensions, so it made sense that crystals would follow those rules, but the universe is often more clever and more mysterious than we imagine. What if a pattern could repeat not just in space but in time? This is the incredible idea behind a time crystal. It's a new phase of matter. It's not a solid, a liquid, a gas, or a plasma. It is something entirely different. A time crystal has a structure that repeats in time. Its atoms move in a regular, repeating cycle, all without using any energy. Think of a clock that ticks forever without needing a battery. The atoms in a time crystal are in constant periodic motion. They oscillate back and forth, returning to their original state at regular intervals. This ticking happens on its own, a fundamental property of the system itself, a rhythm woven into the very fabric of this strange matter. So how is this different from something like a pendulum? A pendulum swings back and forth, which seems like a repeating pattern in time. But a pendulum needs energy to start swinging, and eventually, due to friction and air resistance, it will slow down and stop. It loses energy to its environment. A time crystal is different. It exists in its lowest possible energy state, what physicists call its ground state. Yet, it still moves. It breaks the rules we thought governed everything. It has perpetual motion without violating the laws of thermodynamics because it doesn't produce any useful work or energy. It just ticks. This concept might sound like it comes from science fiction. In fact, it was first proposed in 2012 by Nobel Prize-winning physicist Frank Wilczek. He asked a simple but profound question. Can we have objects whose lowest energy state is one of periodic motion? At first, many scientists were skeptical. The idea of something moving forever in its ground state seemed to break fundamental laws of physics. But the cosmos is full of surprises. After years of theoretical work and experimentation, scientists proved that time crystals were not just a mathematical curiosity, they were real, and their existence opens up a whole new chapter in our understanding of matter. How do you build something that moves forever? You can't just mix some chemicals in a beaker. Creating a time crystal requires some very clever physics. Early experiments were complex. They involved trapping ions with lasers and cooling them to temperatures colder than deep space. These were incredible achievements, but they were difficult to work with and existed only in extreme laboratory conditions. To make a time crystal, you need a system of particles, like the spins of atoms, that are all interacting with each other. This system also needs to be a little bit messy, what scientists call disordered. The disorder helps the particles get locked into their strange, time-repeating dance. The next step is to give the system a little push. Scientists use an external drive, like a laser pulse, to nudge the particles. This is the tick that sets the talk in motion. Imagine pushing a child on a swing. You push them at a certain rhythm, say every 2 seconds. But in a time crystal, the system responds at its own, different rhythm. You might push it every 2 seconds, but the particles might flip their spins only every 4 seconds. This is a key signature of a time crystal. It doesn't just mimic the push it receives, it adopts its own independent and robust period that is a multiple of the driving period. This special response is what makes a time crystal so stable. The system locks into its own unique rhythm. Even if the laser push isn't perfectly regular, the time crystal's ticking remains incredibly precise. This robustness is crucial. It means the time crystal isn't just a fragile laboratory curiosity, it is a genuine, stable phase of matter, just like a solid or a liquid. The particles work together, creating a collective, synchronized oscillation that persists through time. It's a symphony where every atom plays its part perfectly, not because a conductor is telling it to, but because the laws of physics demand it. For a long time, these amazing objects could only be made in highly controlled, ultra-cold environments. This limited their potential. It's hard to build new technologies if they only work near absolute zero. The quest was on to find a way to make time crystals that could survive in the real world, at room temperature. This would be a monumental step forward. It would take time crystals from a fascinating theoretical concept and bring them into the realm of practical possibility. The challenge was finding the right material and the right technique to make this happen. The big breakthrough came when scientists found a new way to create a time crystal. They didn't need a giant complex setup with lasers and vacuum chambers. Instead, they found a system that could work right on a lab bench at room temperature. The secret was in a material with slight imperfections. Scientists used a system of electron spins within a diamond. These spins can point up or down like tiny magnetic needles. By introducing specific defects known as nitrogen vacancy centers into the diamond's crystal lattice, they created a disordered system perfect for hosting a time crystal. This was a game changer. The process was surprisingly straightforward. The scientists used electromagnetic waves like microwaves to pulse the spins in the diamond. This was the external push. Just as predicted, the system of spins responded by flipping at a different, slower frequency. They pushed the system, and it pushed back on its own schedule. They had created a room-temperature time crystal. It was a stable, ticking system that existed under normal conditions. This discovery, announced in 2021, was a huge milestone. It made the creation and study of time crystals much more accessible to scientists everywhere. Why is a room-temperature time crystal so important? Think about computers. The first computers filled entire rooms and required massive cooling systems. Now you hold a device thousands of times more powerful in your hand. Making things work at room temperature is often the key to turning a scientific curiosity into a useful technology. By creating a time crystal that doesn't need extreme cold, scientists have opened the door to exploring its properties and potential applications in a much more practical way. It's the difference between a delicate ship in a bottle and a sturdy vessel ready to explore new oceans. This achievement changes our perspective on what a time crystal is. It's not just an exotic state of matter that can only exist in the coldest corners of the universe. It's a phenomenon that can be coaxed into existence within a common material under everyday conditions. It shows us that the weird and wonderful rules of quantum mechanics are not confined to isolated labs. They are all around us, waiting to be discovered. This breakthrough makes the abstract idea of a time crystal tangible and brings its potential future applications one giant leap closer to reality. So what can we do with a clock that ticks forever? The potential applications of time crystals are vast and exciting, though still in their early stages. One of the most promising areas is in quantum computing. Quantum computers are incredibly powerful, but they are also very fragile. Their calculations can be easily disrupted by the slightest noise or vibration from the outside world. Time crystals, with their incredibly stable and robust oscillations, could be a solution. They could be used to create ultra-precise clocks to time the operations within a quantum computer, shielding them from external interference and making them more reliable. Another potential use is in developing highly sensitive sensors. Because the ticking of a time crystal is so regular, even a tiny disturbance could change its rhythm. Imagine a sensor that could detect minute changes in a magnetic or gravitational field. A time crystal-based sensor could be so precise it could detect a passing submarine from far away, or be used in medical imaging to get a clearer picture of what's happening inside the human body. Their inherent stability makes them perfect candidates for measurement devices that need to be both incredibly sensitive and reliable over long periods. Beyond quantum computing and sensors, time crystals could fundamentally change how we store information. In a conventional hard drive, we store data by changing the magnetic properties of a material in space. With time crystals, we might be able to store information in the time domain, using different ticking patterns to represent ones and zeros. This could lead to entirely new forms of memory storage that are more stable and potentially more dense than anything we have today. The possibilities are still theoretical, but they highlight how this new phase of matter could revolutionize technology. The discovery of time crystals is more than just a scientific curiosity, it is a profound shift in our understanding of the universe. It reminds us that there are still fundamental aspects of reality we are just beginning to uncover. We thought we understood the phases of matter. We thought we understood the relationship between energy and motion. Time crystals challenge these assumptions and force us to think more deeply about the nature of time, matter, and the quantum world. The journey has just begun, but one thing is clear: the universe is ticking with possibilities we never dreamed of.